Okay, so yeah, we realized that one of your friends warned me that we made a mistake here. U and V should be, or X and B, no, A and B should be replaced, right? Our function is positive on B, negative on A. Therefore, the subset U contains B and the subset V contains A. So this should be fixed. We fixed it over the text. Now let's continue. Okay, or let me first write this as a proposition, what we have proved. So let A and B be closed and disjoint subsets of a metric space XD. Then there are open subsets, open disjoint subsets U and V of X, so that A is in V and B is in U. And these are disjoint subsets. So this is what we have proved above. All right, now we will okay, we will start a new topic. Let me write definition. A function between two metric spaces let's write f x to y, x and y are metric spaces, is called a homeomorphism. If f is a continuous bijection, so it is one-to-one onto continuous with continuous inverse. So f is a setwise bijection. It's a one-to-one onto function, so that both f and its inverse are continuous. Okay. In this case, we call the function a homeomorphism. So here is the definition of a homeomorphism. Okay. Okay. Another definition. A function f from x to y, or maybe I should write like this, xd to y rho, is called an isometry if it satisfies the following. If the xy is equal to rho of f of x f of y for all xy in x. Okay. In other words, if this function, preserves distance between points, then we call it an isometry. Let me draw you a picture. So here is, let's say, the space x. Here is y. I have this function. So whenever I have 2 points here, x and y, I measure the distance between these two. And what we see is that if this is f of x and this is f of y, the distance between these two is the same as the distance between x and y. Okay, if this holds for all x and y, then we say that f is an isometry. So it preserves the metric, right? It preserves the metric. Clearly, an isometry remark, right? Taking delta to be epsilon, we see that an isometry f from x to y is uniformly continuous, right? It is continuous, but it is actually uniformly continuous, right? Because it just preserves the distance. Whenever you give me an epsilon, I just choose my delta to be epsilon. Then if x and y are delta close to each other, then they are epsilon close to each other. Their images will be again epsilon close to each other because these two distances are the same. So any isometry is continuous. And if I have an isometry which is also one-to-one and onto, moreover, if f x to y is an isometry and a bijection, so if it is one-to-one and onto, then its inverse f inverse from y to x is also an isometry. Why is that? Well, you see, distance between so whenever I take 2 points y1 and y2 in y, then since f is an bijection, y1 is f of x1 and y2 is f of x2 for some x1, x2 in x. But then, since f is a isometry, distance between y1 and y2 is the same as the distance between, because y1 is just f of x1, y2 is just f of x2. This is the distance between these two. But what is x1 and x2? x1 is just f inverse of y1 and x2 is f inverse of y2. So whenever I take 2 points in y, the distance between these 2 points is the same as the distance between their images under f prime. And this implies f inverse is an isometry. Okay, so that's the explanation for this statement here. So if I have an isometry which is also a bijection, then its inverse is also an isometry. In particular, its inverse function is also uniformly continuous, and therefore it is continuous. Uh, as a conclusion, as a conclusion, a uh, isometry, uh, which is a bijection, also a bijection, is a homeomorphism, because both the isometry and its inverse are continuous. Okay. Okay, now I have one more definition, which is actually something we have seen when we are discussing real numbers. And here is the definition. A subset A of a metric space xt is called dense if what happens if its closure is equal to x. Right, we had the same definition when we studied real numbers with absolute value metrics, so we just carry over this definition to an arbitrary metric space case. A set is called dense if its closure is equal to the whole space. Okay. Example, of course, examples. You see, Q is dense in R, right? What else? Okay. R minus, let's say, 0. If I just take 0 outside R, this is dense in again R, right? Yeah, that's it for now. Two examples. Rational numbers, sorry, irrational numbers are also dense and so on. Okay. Uh, Here is a proposition which relates dense sets with continuous functions. Uh, a continuous function f from x to y is determined by its values on a dense subset of x. Okay, what does this mean? Uh, a continuous function is determined by its values on a dense subset of the domain metric space. For example, a continuous function on real numbers is determined by its values on a dense subset, let's say rational numbers. So, if you have a continuous function on R, then and if you know its values on rational numbers, then you know the values of this function at any point. And the proof is very simple, actually. Just characterization of closure and definition of continuity is enough. So let me reformulate the content of this proposition. So we have to prove the following. Uh, let f and g be two continuous functions and a dense subset. A dense subset. I have two continuous functions, and we assume that these two continuous functions agree on this dense subset. Assume that f of x equals g of x whenever x is in A. So these two functions agree on this subset A, which is dense. The proposition tells us what? Then we must show f equals g for all x in X. Okay. In other words, if they agree on A, then they have to agree on X. Okay. That is the content of this proposition. A continuous function is determined on its values on a dense subset, no matter what the dense subset A is. If you have a subset A, and if these functions f and g agree on A, then they have to agree on the whole metric space, provided that, of course, f and g are already defined on X and they are both continuous. And the proof is very simple. How can we prove this? So I said we must show, right? So let x in uh, any point in X, which is a closure because A is dense in X. But what was the sequential characterization of closure? Then there is a sequence xn in the subset A with limit xn is equal to x, right? A point is in the closure if and only if there is a sequence in the set A which converges to that point. All right. But then we have what? Now, since f and g are continuous, we get what? F of x, which is equal to what? Limit f of xn as n goes to infinity, right? This is just being continuous, right? If I have xn converging to x, then f of xn converges to f of x. And by assumption, f and g agree on A. So whenever xn belongs to A, then f of xn is equal to g of xn. Therefore, I can replace f of xn by g of xn because they are the same. However, g is also continuous and xn is converging to x. Therefore, this limit is equal to g of x. So we have obtained that f of x is equal to g of x. Okay, which finishes the proof. Okay. So whenever you have a continuous function and if you know its values on a dense subset, then actually you know the function, okay? Do you have any questions so far? All right. Uh, Now we will have a slightly different result now, but it is a little bit different. Now let me talk about that. Let me state the result, which resembles the above result, but actually it is quite different. And we will make use of almost everything we have built so far. Okay, so let's, and you will realize this once I write down the statement. Let Y row be a complete metric space. Metric space. A a dense subset in X and F0 from A to Y. Uh, so X is another metric space. A is a dense subset of that, and F0 a uniformly continuous function. Okay. Then the statement is the following. Then there is a unique uniformly continuous function f from x to y such that f and f0 agree on uh, for all x in A. Further, if f0 is an isometry, then so is f. Okay, so this result tells us a lot of things. Let me go over it. So I have a complete metric space Y and another metric space X, and we have a function defined on a dense subset of X. Let's say F0, which is uniformly continuous. Okay, uniformly continuous. The statement is this. Then I can extend the domain of this function to whole metric space X. It was defined on A. Now I can extend its domain to X. In other words, I can find a function defined on X, which is again uniformly continuous, so that F and F0 agree on A, right? This is just the definition of extension of F0, right? F is an extension of F0 if F and F0 agrees on the smaller set A. The important part here, if f0 is uniformly continuous, then f is uniformly continuous. Moreover, such an extension, it exists, but it is also unique. So there is only one such f. Okay, and further we have the following: if the function f0 were an isometry to start with, then its extension is also an isometry. Okay, so that's the content of the proposition. It will take some time to prove this. It is not that easy, but we will go step by step. The basic idea will be this. So maybe let me give some examples or non-examples where this holds or doesn't hold. Examples, or let me give one example first. Consider this function, for example. So let's say x is the real numbers with absolute value metric, okay, and y is the set of real numbers again with absolute value metric, and a to be this, okay, let's say a to be the rational numbers, okay, and consider this function from a to y, so from, okay, q to r, defined by this: f0 of x is just 1 over x minus root 2. This function is well defined. Why is that? Because, you know, the denominator is never 0, right? X is a rational number, so x minus root 2 is never 0. Therefore, this function is well defined. Moreover, it is continuous. Why is that? Because x minus root 2 is continuous. 1 over a continuous function is continuous. The denominator is never 0. So this function is continuous, right? f0 is clearly continuous. I don't say anything about uniform continuity of this function. The reason will be clear in a moment. Okay, now I ask the following. Can we extend the domain of this function to the set of all real numbers, right? It's a continuous function, so, you know, why not, you know, extending this function to all real numbers? Well, if you extend this uh, function to real numbers, then as a real number, root 2, I should be able to plug that number, root 2 here. But because of continuity, right, at root 2, the value of this function should be 1 over root 2 minus root 2. And in that case, the denominator will be 0. So you see, this function, however, this function cannot be extended to r as a continuous function, right? Why is that? Because, you know, as I said, if there is a if it were, right, uh, then I should be able to plug root 2 here, but in that case 1 over root 2 minus root 2 would be 1 over 0, so it that's a problem. So this kind of looks like a contradiction to the above proposition, right? In this proposition, we say that there's always an extension, and it's a unique extension. The important thing is this. Here, you see, uh, I set a uniformly continuous function, and this function is not uniformly continuous. So this is not a contradiction, because f0 is not uniformly continuous, right? The graph of f0 is something like this, right? It is an asymptote, right? It's something like this. It is defined on only rationals, but it's, graph is something like this. Or maybe even I can call this A to be not this, but let me make it even simpler. Just take A to be this set, okay? Everything except root 2. Now it is even more easy to see why this is continuous and why it cannot be extended to the real numbers. Its graph is like this. Clearly, you cannot just complete this graph to a graph of a continuous function defined on the all real numbers, okay? And this function is not uniformly continuous. Why is that? So you see, whenever you take an epsilon like this, uh, if you choose your, and so if you choose epsilon like this, let's say 1 unit, and whenever I am given some delta, if I just move this delta interval closer and closer to root 2, then the, uh, distance between the y coordinates of these values will get bigger and bigger, and it will exceed my epsilon. So no matter how delta is small, how small delta is, if I move these points toward root 2, the distance between these two values will be get bigger and bigger. Actually, that distance will go to infinity. Therefore, it will exceed epsilon, which is, let's say, 1 unit. Therefore, this function is not uniformly continuous. So this, of course, tells us what? In the proof of the definition, we have to make use of uniform continuity. Okay. Another example, actually again a non-example, is this. Consider this function again. So x and y again are, and let's take a to be this, and let's consider this function from q to y, which is r. So a to y, q to r, f0 by f0 of x is just x, just identity function. It takes x to x. Clearly f0 is uniformly continuous. Clearly, I'm sorry, I made a mistake. Let me say, okay, a is q, and y is also q. Okay, yes. Now, so this is q. From q to q, there's no problem. This function is well defined. It is the identity. Clearly, f0 is uniformly continuous. Can we extend q to r? No, because, okay, rational numbers is mapped to rational numbers. What about root 2? Where will be root 2 mapped? Well, root 2 should be mapped to root 2, but there is no root 2 here, right? This is the set of rational numbers. Clearly continuous. However, f0 cannot be extended to real numbers, okay? Because there is no space, enough space in Q, right? This function is identity. It should extend as identity, but what about irrational numbers where they will be sent, right? And the reason actually is the following. I said there is no room for irrational numbers here, and the reason is that Q is not complete, okay? Because Y, which is Q, is not a complete metric space, okay? So you see, for the proposition to hold, I really need the assumption that Y is a complete metric space and F0 a uniformly continuous function. So in this proposition, we have to make use of this assumption that this is complete and this is uniformly continuous, okay? These are important assumptions. If you drop them, then the conclusion doesn't hold, okay? So we have to make use of these. Okay. Now, evet. Complete olup uniform sıfırın mı? Tabii var. Consider the function from R to R, just x square function. It is not, it is continuous but not uniformly continuous. Ama şey diyorsan hani proposition'da sıkıntı çıkartır mı? Çıkartabilir. Yani o uniformly continuous olması gerekiyor orada. Gerekmiyor da yani o olmazsa işler zorlaşıyor. Okay. Now, for the proof, so we have what? F0 from A to Y is uniformly continuous. This is given. Continuous. This is given. Another thing which is given, Y row is a complete metric space. And the third thing is that A is dense. Okay, its closure is equal to A. A is dense. Okay, now I said there is a unique extension of F0 to whole metric space X. First of all, I have to construct that extension. Suppose our function is defined on Q. I know its values at every rational number. Then I have to somehow guess the value of this function at an irrational number like root 2. What will be the value at root 2? So how can we do this? So existence of uh, the extension f from x to y. First, let's consider this part of the proof. Okay, the idea is this. At an irrational number, always keep in mind that, uh, we are in the following situation. X and Y, let's say, are real numbers, and A is the set of rational numbers, and I have a function defined on rational numbers which is uniformly continuous, and I want to extend this function to all real numbers. So I want to define it at an irrational number like root 2. How can I do this? Well, of course, we have to use our tools, and in this case, since we have continuity, metric spaces, and complete metric spaces, we have to make use of sequences. Root 2 is an irrational number, but there's a sequence converging to that, consisting of rational numbers, and I can use that sequence to define f. And the idea will be the following. Of course, I have to use sequences, convergent sequences, and in this case, they are also Cauchy. Well, they are always Cauchy. And once you have a complete metric space, then those Cauchy sequences will be convergent also. And since f is uniformly continuous, what it does, it sends close points to close points. Delta close points are mapped to epsilon close points. And that will imply the following. If you have a Cauchy sequence, then its image under a uniformly continuous function is also a Cauchy sequence. Okay, so that's an important fact. So first I have the following claim. Whenever xn is a Cauchy sequence, in A, then f0 of xn, right? Uh, f0 is defined on A, so take uh, I can consider its values on xn, so I get a sequence in Y, and this sequence is a Cauchy sequence, in Y. Let's see first this proof. So let epsilon be given. Okay. I want to show that this is a Cauchy sequence, so I have to find an index, right? But first, f0 is a uniformly continuous function. Since f0 from A to Y is uniformly continuous, there is some delta positive, so that uh, dxy is less than delta implies rho f0x f0y is less than epsilon, right? This is the definition of being uniformly continuous. Okay, now if I can make the terms of my sequence then delta close to each other, then their values under f0 will be epsilon close. That's what I want, right? And I can make the terms of the sequence xn delta close to each other because xn is a Cauchy sequence, right? Now, since xn is a Cauchy sequence in A, Therefore, in X, there is some index n0 so that m and n larger than n0 implies the xn xm is less than delta. I use this positive real number, but then uh, if this is if the distance between xn and xm is less than delta, then the distance between their values will be less than, right, f0 xn and f0 xm is less than epsilon whenever m and n are larger than n0. So we have proved what? Remember, my aim is to show that this is a Cauchy sequence f0 of xn. So I started with an epsilon. I found some n0 so that if m and n are larger than n0, then this distance is less than epsilon. Right, so we are done. Hence, f0 xn is a Cauchy sequence. In Y row metric space. Okay, so this is a technical result claim, but it will be very important in the construction of this function. How? Let me, if I have time, well, I don't have much time, but let me just give you the idea. Okay, definition of f from x to y. We will define it this way. Take any x in x. It doesn't have to be an element of a. It's an arbitrary element in x. But since a is dense, so a closure is equal to x, there is a sequence xn in a. Okay, this sequence lies in a with what? Limit xn is equal to x. All right. So xn is a convergent sequence. Actually, it's a convergent sequence in x, but it is not convergent in a because the limit point may not belong to a. But in any case, it's a Cauchy sequence in x and a Cauchy sequence in a. In particular, xn is a Cauchy sequence in AD. But we have just seen here that if I have a Cauchy sequence in A, then its image is a Cauchy sequence in Y. Right? We just proved that. Hence, f0 of xn is a Cauchy sequence in Y row. Well, Y row is a complete metric space. Therefore, every Cauchy sequence is convergent. Since Y row is a complete metric space, metric space, the Cauchy sequence f0xn must be convergent. And we define, now we define, I would like to define the value of f at x0 at x as, we define f of x as this. Here is the definition. The limit of f0 of xn as n goes to infinity. Since it is convergent, its limit exists, and I define f of x as this limit. But you should immediately object to this definition, right? Why is that? Well, I use some representatives to define this value. Which representative? Whenever I pick I picked an element x, but then to define its value, I used a sequence xn in A converging to x. What if somebody takes another sequence converging to x and use that sequence to define the value of f? Would I get the same limit? If I don't, then this won't be a well-defined function, because depending on the sequence you choose, you get different values, and that's not something acceptable, right? The value of this function at a point should be a specific fixed value. It shouldn't depend on the people or the sequence, the people, the person who chooses uh, that sequence so that it converges to x, right? So this is not done yet. We have to prove. So next time we have to prove the following: show that to show that f is well defined, we must prove what? We must prove the following. Okay, if yn is another sequence with limit yn is equal to x, then limit of f0 of yn as n goes to infinity should be the same as the limit of xn. So this will show that it doesn't matter which sequence you choose converging to x. Either you choose xn's oryn's, okay? This limit will be always the same. Therefore, this definition is acceptable, okay? It doesn't depend on the sequence you choose to define this function. So next time I'll prove this fact, and then as you see, we are not done yet, right? We have to do a lot of things. I claim that f is uniformly continuous, so we have to show that this function f is uniformly continuous. Also, we have to show that it is unique, right? We say that such a function is unique. That part will be easy. And finally, we have to show that if f0 is an isometry, then f is an isometry. So there are several steps we have to complete, and we will do it next Tuesday. All right. See you then.